Welcome to Chapter 8 of Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow. My name is Shashank, and I'm a data analyst on my journey to become a data scientist. Every week, I go over a new chapter in this book and then try and compile all of my learnings into notes and code that I go over with you guys in video format. So this week, we're going over Chapter 8. Before we get started, I'd like to take a chance to plug my Patreon. My Patreon is just a great way to support me, and all of the code and notes that you will see in this chapter are available on it. Of course, I'm going to be going over all the notes and all the code in this video as well, so the knowledge is available to everyone. But if you want to support my work, my Patreon is a tremendous way to do so. If you're not able to do so, or you do not wish to support my Patreon directly, that's totally fine. A like, comment, and subscribe is another great way of showing YouTube that my content is worth watching. Comments and likes are especially helpful because subscriptions are not as important anymore in YouTube. They're more just for us to see, like, generally, is our channel growing or not. But at the end of the day, views, likes, comments are what are most important to YouTube. So that's a great way to support my channel. So without further ado, let's go ahead and get started. I know you guys mentioned that you like it better when I live code, so I'm going to be doing a little bit more of that this time. So I've already written out all the code, but I'm going to be coding it live as we go along, as I go through the chapter to show you guys what exactly we're doing. So what is this chapter? Chapter 8 is about dimensionality reduction. And if you have been keeping up with what we've been doing so far, you'll know that oftentimes in machine learning applications, we'll have a table, and in that table we'll have multiple columns, and each of those columns represents a feature or a dimension. So for example, if you have a data set with 4 columns where one of them is the column you're trying to predict, that's a 3-dimensional data set. It has 3 features and then one column you're trying to predict. So when we go through dimensionality reduction, what we are trying to do is we're trying to compress the number of features from, maybe 30 to 100 to 500 down to maybe a couple of dozen or even, a couple of hundred if you have enough features. In sufficiently complicated machine learning applications, you'll see that people tend to have like hundreds of columns, and you can imagine why we may not want to actually model on all of those columns. 2 main reasons that you want to use dimensionality reduction. One is because you might want to visualize your data, and you can't really visualize data outside of 4 dimensions, and I'll show you what I mean in a second. And 2, because you can't, you might have difficulty putting a large amount of data into a machine learning algorithm without intensive computational resources. And the benefit you might get from the last 100 columns may not be worth modeling on the extra 100 columns. So those are the 2 main reasons you'll want to reduce your dimensions. So let's get started with the chapter. So first, they go over something called the curse of dimensionality. And if you have a lot of dimensions of your data, then oftentimes your data becomes very sparse. And what they say is that in real life, data tends to be sparser as you increase the number of dimensions. What that means is that the actual amount of information that you can actually model on contained per column reduces as you add more and more columns. And so dimensionality reduction tries to find the different subspaces in your data that have the most information in that. And we'll get to what subspaces mean in this context in a second. So one solution to the curse of dimensionality is to have more training instances, but the number of training instances we need grows exponentially with the number of dimensions. So every time you add in a dimension, for example, right? So imagine I have a data set, and actually let me just go ahead and I can even pull up a Excel file right here. And let's say we have feature 1, let's say feature 1, feature 2, and feature 3. And then let's go ahead and say we have row 1, row 2. Well, and actually, let's just use the Excel column or Excel row numbers to count. You'll notice that if I have, for example, let's say I have 4 rows of data, right? So rows 2 through 5. If I was to add another dimension, so if I go F4 over here, then I just added another 4 records of data. So every time I add a new dimension, every time I add a new either dimension or line of records, I'm adding a tremendously larger amount of data to our data set, and then it increases exponentially as time goes on. So as you can see, if we add a training instance down here, every time we add a dimension, that's just another set of training instances, another column of training instances we need to add. Basically, this could lead to a problem where you have way too much data to train on, and that becomes a real issue if you do not have the computational resources in order to handle all that data. So there are a couple of main approaches towards dimensionality reduction. There's something called projection, there's manifold learning, and then we'll go over PCA, the actual like ways we handle it. So what projection does is it takes the assumption that in real life most dimensions are not great predictors of training instances, and training instances will lie within a subspace of a couple of dimensions that are more predictive of anything than anything else. So what do I mean when I say that? Well, let's take a look at this graph over here. You'll see we have a three-dimensional space over here. And what might happen is that even though this is a 3D space, this plane over here contains most of the data. And how do we know that? Well, if we look at the, let's call it the X3 axis over here, you'll see that the points actually don't have a lot of space in between them, meaning that there may be like 1 or 2 unit, or well, 0.25 units away from this plane that we've drawn. And by creating this plane and then plotting every single, like removing the X3 axis and just like flattening everything onto that plane, we have removed an entire dimension from our calculations and have not lost a lot of information in the process. And that's the thing about dimensionality reduction. You're always going to lose some information, but it's all about determining, okay, how much information loss is okay relative to the amount of data I have to process. So that's what we're going to be, that's what we try to minimize. We try to minimize information loss while also minimizing the amount of total data that we have to process. Now, another thing you might see is something called manifold learning. And what manifold learning is that it takes into account the idea that maybe you can't draw a plane like this on the data. So this, they call it the Swiss roll data set, is a really common data set to use this on. If you were to just use manifold, or if you were to just use projection, right? So if you look at this graph down here, X1, if you were to take all of the different points and you were to squish them down onto one plane, then you wouldn't be able to separate out the points, and this is not a great representation of our data. Versus, for example, if you were to create a manifold, I'll go over what that is in a second, where you have these dark points over here, the red points over here, and the yellow points over here, you'll see that this is a much better separation of the data points than you see over here. And what is a manifold? So a manifold is basically, it is a method, it is when you are able to take a shape of some kind, a shape of a lower dimension, and twist it in a certain way to fit a higher dimension set of data. So what do I mean by that? Okay, so we look at the Swiss roll over here, right? This is a 3D shape. But if I were to take a 2D plane and fit it inside this Swiss roll over here and twist it in such a way that it fits inside that Swiss roll, that is a manifold. I've taken a 2D plane and then I've like twisted it inside a 3D plane, and then when I project all the points onto that and then flatten it out, I get this over here, which is significantly better than just having a flat plane and then projecting all the points onto it. I highly recommend looking at the chapter yourself as well, and I recommend that with all of these videos that I do. You should definitely read the chapter yourself, and the videos I make are kind of just a summary of the content in that chapter. But I recommend looking at the chapter because if you're not familiar with dimensionality reduction, so much of it is based on this idea of being able to visualize the data in your head that I think reading over the chapter at least once or twice is very helpful in helping you do. Now, one thing about manifold learning is that this kind of assumes that a manifold is the simplest way to split your data. But if you look at this over here, this figure we have over here, again from the book, you'll notice that these green and yellow dots over here are much more easily split by a flat plane that we just project all of our points onto. And if you put that flat plane, you slice it in between that Swiss roll over there, then that's much better than creating a manifold. And you'll see that they just put the plane over here, this blue line, versus creating a manifold. Or for example, you'll notice that over here, all the green points are anything past x1 equals 5. That's where you have all your green points. And you'll notice that anything past x5 goes in this direction to the right. It makes much more sense for us to use a projection method rather than a manifold method in this instance. So that's kind of the theory behind it. Now let's go ahead and see if we can do some actual applications. So principal component analysis is by far the most popular dimensionality reduction algorithm. And what it does is that it identifies a hyperplane that lies closest to the data and projects all of the data onto it. And the thing is, because we can't really visualize data outside of 4 dimensions, really 3 dimensions, but 4 dimensions, and I'll tell you what I mean when we start coding in a second. But because we can't visualize data outside of 3 dimensions, you kind of just have to you have to remember that a computer can not visualize, but a computer can deal with data in like an infinite number of dimensions. And honestly, we wouldn't use PCA on 3D data. We would most likely use it on like data with like 50, 60, 100 columns and data that's like maybe 1,000 dimensions, or some where n is really high number of dimensions. And the reason for that is because, again, we lose information whenever we add it whenever we remove dimensions. So you want to reduce dimensions as little as possible in order to lose the least amount of data possible. So when selecting the hyperplane to project your data onto, you'll want to select a plane that preserves the most variance in the data, because the variance is where your information will lie. So for example, if we take this data over here, you'll see that there are 3 different hyperplanes that they picked. And I believe C1 is the one we're looking at over here. You want to pick C1, which is this diagonal line over here, because it spreads the data out the most and gives us the most variance, which allows us to actually see the differences in the data. So for example, imagine we went with this third one over here, which is, this would be if you had this hyperplane over here, the dark square line one over here. As you can see, there's hardly any difference in the data, and I can't really tell what's going on and what makes the data different from each other. Because at the end of the day, if you think about it, what are we trying to do with data analysis? We're trying to find variance in the data and then use that variance in order to obtain information. So for example, when fraud detection is an amazing application of machine learning and an amazing application of data science, you're not trying to find the person who uses their credit card regularly. You're trying to find the person who uses their credit card irregularly. Basically, where's the variance? So variance is exactly what we look for in most machine learning applications. And that is why you want to find the hyperplane that gives you the most variance. And in this case, it would be the hyperplane defined by C1, vector C1 over here. Now, why they use vectors, I'm not 100% sure. I think this is where you start getting into linear algebra, which is at least currently beyond what I fully understand. But they do use vectors. I just kind of think about it as like, okay, like what line can you have that has the most variance in it? So after you calculate the principal components, you can then create a hyperplane of d dimensions by selecting the number of principal components as dimensions you want and then projecting the points onto that hyperplane. And let's go ahead and let's get into the code. So I'm going to open up a Jupyter notebook, and we are going to use a specific data set. So this is a credit card data set. So this is from the machine learning group -ULB on Kaggle. And if you just go to this URL over here, you'll be able to find the data set that I'm using. It's a relatively large data set, and it will have enough dimensions for us to actually do some kind of a reasonable PCA on. So let's go ahead and do our normal imports first. So let's go ahead and say import pandas as PD, and then import numpy as NP. And then I'm going to run this on my hands-on ML environment. And the hands-on ML environment just has scikit-learn, plotly, pandas, numpy, just your basic stuff over there. And for those of you that don't know what plotly is, stick around. Plotly is an amazing graphing library inside Python and way better than matplotlib in most cases, and I'll show you why in a second. Get some water. All right, so let's go ahead and import our data. So data underscore import equals pd.read.csv, just reading our CSV, credit card.csv. And then let's go ahead and take a look at it. So you can see we have 284,000 rows and 34 columns. So 184, 1, 2, 3 times 31. You can see that is 8.8 million records. So, not an enormous data set, but definitely not a small one. So that's why I wanted to use this one. And I mostly wanted to use this one because of the number of columns that we have. 31 columns is a lot of columns to work with. And this is an example of where PCA might be useful. So let's go ahead and get started. So the first thing I want to do is I want to only include these V's over here. So these V's are basically your features that you care about. Amount and class I don't really care about, and time I don't care about. So let's go ahead and put unused columns. And then we'll say that equals data import, time and amount. So we're not going to be using that. And then let's go ahead and create our Y, and our Y is going to be class. 0 stands for a non-fraudulent transaction, and 1 stands for a fraudulent transaction. So let's go ahead and do Y equals data underscore import, and then we'll say class, and then we'll say X equals basically everything else. So data import dot iloc, so index, is it index locator? I don't know, index something. And then we want all of the rows, and then we want columns 1 through -2. Of course, using negatives meaning that it starts counting backwards. and let's see what we have. So we have data going starting from V1 going up to V28. And that sounds about accurate. Perfect, perfect. Cool. All right, so let's go ahead and start doing our PCA. So I am going to start off with a very basic PCA. So from Scikit-Learn.decomposition, import PCA. All right, so that's our simple import. And then we do PCA equals PCA n components. So n components would refer to basically how many dimensions we want to reduce into. So basically how many components do we want in our principal component analysis. And I probably should have said it earlier. PCA stands for principal component analysis. So n components equals, let's just say, 10. And then we just do x10d, meaning x 10 dimensions, equals PCA.fit transform. And as you can see, this just follows the standard format of all scikit-learn libraries. And then let's see what x10d looks like. PD dot, I'm going to turn it back into a data frame because it creates a numpy array that's super ugly. And I want to avoid that. X10D. Oh, and I should probably put X10D over here so we can go ahead and take a look at it. And as you can see, we were able to reduce our 31 columns, or I guess 28 columns, down to just 10 columns. Okay, so that was just to show you how easy it is to perform a PCA. Let's go back to the notes and actually start looking at what we did over there. So as you can see, we just went ahead and reduced the amount of data we have from 28 columns down to 10 columns. And what we want to, there's a couple of questions we might ask ourselves over here. The first one is, okay, how much of the information, if we say variance is information, how much of the variance have we lost in doing this process? So you can do that by using the explained variance ratio method, or I guess isn't it a method? Oh, no, I guess it's a variable. So the explained variance ratio variable will tell you exactly what percentage of the variance is explained by each principal component. And one thing I should probably mention is that the first principal component will have the most information, then the second one, then the third one, then the fourth one, then the fifth one. So each principal component you have will subsequently have more and more information than the previous one, meaning that the first 5 will have more information than the subsequent 5 after that. And how do we see how much variance and how much information is actually contained inside each of these PCAs? Well, we can go ahead and just run the code over here. So we are going to, let's go ahead and copy this. Whoops, copy. And then we are not going to set this variable over here at all, the number of components. So we're not going to specify the number of components. So I think it should just have it'll just have the total number of components that we had earlier. And then I just want to do a regular fit method over here. And we'll just call XD for X dimensions. And then we will do cumulative sum. So the cumulative sum equals np.cumulative sum of PCA dot explain variance ratio. All right. And then D will equal the maximum argument. So np.argmax of the cumulative sum that's greater than or equal to 0.95. So as you can see, what I'm doing over here, right, is I'm asking NumPy to tell me, and I'm asking sklearn NumPy to tell me, okay, how many dimensions do we need in order to explain 95% of the variance in this data? And let me illustrate what I'm talking about over here. So if you look at the cumulative sum variable that we created, you'll see that it's a NumPy array, basically just meaning a list, that cumulatively adds from 0 to 1. And each of these represent I think this should have like 28, should have 28 items in it. Yep, 28 right there. And let me zoom in for you guys. And as you can see over here, what it does is for every single column in our data, for every dimension, it tells us how much of the variance in our data that dimension explains. So for example, the first dimension explains 12.48% of our variance. And then the next one plus the first one, because we did cumulative sum, remember, explains 21%. So that would be about a 9% difference. So for example, the first component, the first variable, or the first component we have, explains 3% more of the difference than the next variable explains, and so on and so forth. And you can see the one after that only explains about 7, and then it's about a little bit less than that, and then it's about 6, and it goes on from there. And we have to go until the 21st component, which is like right here, I believe, before we are able to explain 95% of the variance. What this means is that, again, depending on how precise and how much computational, how precise you have to be and how much computational power you have access to, you could probably drop the last 7 columns of data and just reduce it to 21 principal components and still train a machine learning algorithm that's just as good as if you had kept all of the data. Now, again, we only have 31 columns over here, and I have a relatively powerful computer, so this would not be a example of a time in which we would actually use PCA, but this is just to illustrate, hey, this is a good this is how you would use it, and this is one way we determine how many dimensions do we want to keep. Now, how do you know how many or what percentage of the variation you want to keep? Now that's up to you, and this is where data science becomes more of an art than a science, and this is why people hire data scientists. They don't hire data scientists in order to write sklearn.import xyz. Like the actual machine learning part takes like 5 lines of code. It's all of the experience that you put together and all the experience that you generate that is able to say, like, okay, based on my experience in this industry for the application that we want to do. So for example, if you want to detect tumors versus if you want to predict consumer spend at a retail company, you would have 2 very different metrics as far as like, okay, what is the level of certainty I need? So for example, with if you're trying to predict tumors inside, they have machine learning algorithms these days, specifically deep learning networks, that are able to look at X-rays, or I think it's MRIs of people, and like say, okay, this person has a tumor, this person doesn't, with more accuracy than most doctors can. You might actually want to have an algorithm like that biased towards a false positive, because you want to be, it's better safe than sorry in those cases for most people. Versus if you're working retail and you're trying to, like, predict consumer spend, you may not want to over predict consumer spend, and the variances you have in your parameters over there are going to be significantly different. And that's what you need a data scientist for. As you start implementing this stuff, you'll start to see the patterns in it, and you'll start to see, like, okay, it makes more sense for me to have this kind of variance over here but not this variance over there, and so on and so forth. So you could pick 95, for example, right? Another method you could use is something called the elbow method, which we went over in an earlier video, where basically what I do is, let me go ahead and import matplotlib, and I'll show you. Import matplotlib dot pyplot as plt. I could go ahead and plot this, so plot equals cumulative sum. And what happens is I'm looking for a sharp elbow, after which I would say, like, okay, after here it's diminishing returns, and we might as well just like have our principal components up until here. So you'll see in this data we don't really have a sharp elbow. I'd say like the elbow is probably somewhere like over here, because it does obviously taper off at one point in time. So like your elbow's kind of over here. But in the example they give in the book, you'll see. Oh, I guess I didn't take a screenshot of that. But there's an example in the book where like the elbow is like a lot more obvious, and so that's where you might want to use the elbow method. So you can either specify the amount of variance you want to have, or you can just say elbow method, we're going to do it that way. All right, let's go to the next section. I should mention that, say you, for example, wanted to have the PCA algorithm automatically pick the number of PCAs for 95% accuracy or 95% variance, just tell n components to equal something between 0 and 1, and that percentage is what it'll try and match. All right. So PCA can be used to actually compress the amount of information that has to be plotted or has to be dealt with in your machine learning algorithm. And let's say you perform PCA and you take in all the components that constitute 95% of the variance in the data set. You can then take all of those PCAs and then inverse transform them, like you can with a lot of machine learning algorithms, or like you can with a lot of the pre-processing steps in sklearn. You can inverse transform them and get something close to the original data. Of course, the 5% that you'll be missing, that error, is called the reconstruction error. And you can go ahead and inverse transform your data just by using the inverse transform method. So if I go over here to, I think it's like xd, oh, did I? Okay, let's just say this, x10d. So x10d, okay, cool. You'll see we have our 10 dimensions over here. I can go ahead and do an inverse transform, inverse underscore transform. Wait, can I do it like that? Oh, PCA dot inverse transform, whoops. So what I actually have to do is I have to use the same PCA argument. So let's go over here, back to our 10D example. Let's run it one more time. And then let's do x10d dot, or sorry, x inverse, we'll call it that, equals PCA dot inverse transform our x10d data. And then we get x inverse. And you can see it inverse transformed your data, and whatever you lose is called your reconstruction error. So that's actually another method by which you can determine how many PCAs you want, how many principal components you want. You can do an inverse transform and say, okay, I want a 5% reconstruction error. I want a 3% reconstruction error. Basically, minimize the reconstruction error that you want. That's another method that you can use. So if you have a lot of dimensions in your PCA, then you might want to take a stochastic approach, basically meaning non-deterministic, where your computer will try and estimate your PCAs instead of actually calculating them. And you can do this by setting the SVD solver hyperparameter of the PCA class to randomize. And by default, this hyperparameter is set to auto, which means that the logic is a little bit complicated, but basically it takes a look at your data and it uses a rules-based method to determine whether it should use a stochastic approach or a deterministic approach. So it's normally set to auto. And what happens is Scikit-Learn will run the full PCA unless the amount of dimensions is too high if you have auto on, and then you can force it to run the full PCA using SVD solver with the hyperparameter set to full. And the reason that this is important, and it's not something I can really demonstrate with the amount of data we have today because there's too little data. It really needs to be a massive amount of data. The reason you might want to do this is that a PCA can take a long time to solve if you have enough data or if you have a weak enough machine. So this is why you might want to use the SVD solver method, or hyperparameter, I should say. And then PCAs only work if the whole data fits inside the memory of your computer. Again, this isn't enough data to actually demonstrate that with, but you can use the incremental PCA class in order to actually reduce the amount, or in order to, incrementally feed that data into your computer. That way you can fit it into memory. And you'll see this is one of the problems that data scientists really start encountering at one point in time too. The amount of data they start working with is so massive that just the limits of the computational power they have really start to hit them. I personally have not worked with that much data in a machine learning context, and there was one Kaggle data set I wanted to use. There's this really cool 4 GB data set that's that Jane Street, for anyone that doesn't know where Jane Street is, a hedge fund, I guess. It's some major New York Wall Street firm that they do all kinds of computational trading. It's the stuff they do is really, really cool. And they have a competition on Kaggle where basically they released a 4 GB data set with 100 features or something, and they say predict the stock market with this. It's really interesting. The prize money for winning that is $100,000. So if you're interested, go check it out. But the submissions are over for that. So if you guys remember in the earlier chapter where we were talking about the kernel trick, I think it was when we were talking about support vector machines. If you remember, the kernel trick was just a method by which we could transform a non-linear set of data into a format that a linear algorithm, such as support vector machines, could actually handle. And that's why we can apply that exact same logic to something like PCA, and it's called kernel PCA. So what happens is what we've been running so far is basically a linear PCA, but we could also run a kernel PCA on RBF or on using a sigmoid kernel. There might be more kernels than that, but these are just the ones that we have. These are just the ones that I read about inside the book. So what happens is if you there is one problem that they note in the book is that there's not necessarily a set of rules that tell you, okay, you want to run this kernel with this gamma on your data. And because of that, you might just want to use grid search in order to actually determine, okay, which one has the best parameters. And if I copy this code over here, then you'll see, I'll put it over here and let's run it. It'll do a grid search on using both the RBF and the sigmoid kernels. And these, and then basically, for anyone that doesn't know, np.linspace is basically a NumPy method that creates a range of values based on like how you decide to write the method. So like I'll run this right afterwards and I'll show you how this one works. So it's testing out all these gammas and it's testing out all these kernels. And what it's doing is it's running a kernel PCA and then a logistic regression to try and classify our data. And then telling us, okay, like which one gives us the best, which one has the best parameters inside it. So as you can see, this is actually taking a little while to run because the amount of data I have is actually quite large for the purposes of what we're running right now. And we'll leave that to run while I copy this over here. And basically this is kind of just like brute forcing, trying to figure out, okay, like what are the best parameters for us to run? And remember, a logistic regression, although it's called a regression, remember it's actually a classification algorithm. Very confusingly named, but it's a classification algorithm, not a regression one. Interesting. So this might just be a problem with too much data. Cannot generate requests. Session cannot generate requests. Interesting. Generate requests. Interesting. It just looks like it's some error. So that might have been too much information for it to handle. Oh, I think the entire kernel crashed, like the Jupyter kernel. Yeah, not like RBF or Sigma. I think my Jupyter kernel crashed. So I'm going to get rid of this. Or you know what? You know what we could probably do? Check this out. So let us comment this out. That way it doesn't run right now. And then run everything. Session cannot generate. Yeah, so the entire thing crashed. Oh, shoot. Oh, it's gone. Okay, so I have to restart VS Code. So let us quit this and then run it again. So what I'm going to do now is I'm just going to sample the data and hopefully that will, interesting. Hopefully that will like make it to where we can actually run this without crashing the entire thing again. Data import.sample. So basically it'll just take a random sample and let's just say we want to sample 10% of the data. 28,000 should be more than enough. And then let's go ahead and replace that, replace that, replace that. And then we will uncomment this, save, and then run everything. Oh, it crashed over here. Only integer selected as n value. I thought I could put a float in there. Okay, so let's just do 30,000 records. And then we'll try it again. There we go. Okay, we've sampled our data, 30,000 rows. And let's see if we have a crash over here again. So it is running again. It's running with about 10% of the data. So hopefully this leads to better outcomes than before. And let's see what we have next before. Oh, I guess we can go over this while that's still running. So if you want to make this method truly unsupervised, where basically it picks everything for you, you can pick the kernel hyperparameters that reduce the reconstruction error the most. And because of the mathematical, and there's some, like in the book, there's some mathematical complexities that I don't quite understand. Something about there being like an infinite dimension feature space. You can't perfectly reconstruct a kernel PCA. I'm guessing it has something to do with the fact that like you can transform the data with a kernel, but you can't fully transform it back. and you kind of have to like estimate the backward transformation. And what happens is you can my understanding of what they're saying in the book is that whenever you want to inverse transform it, what it does is you have to specify the fit inverse transform method in your kernel PCA to be true. So you'll see your kernel PCA over here, you specify that fit inverse transform method to be true. And once you do that, it kind of tracks one point from start to finish of this entire method, and then it sees what is the deviation of that point from where it originally was, and then uses that to estimate where everything else should go back to. Again, the math and logic behind this part was a little bit complicated for me, but my basic understanding is that if you want to inverse transform your kernel PCA, then you need to make sure that this method, it basically needs to track the point from the beginning, which is why you might want this method to be true when you do it. Okay, so the fact that this is still running is not giving me a lot of confidence. But if it doesn't work, then we'll just skip over it and go on to the next section. I have something a lot cooler I want to show you guys anyways. And then as usual, I have a couple of other sources inside my notes that are on my Patreon, where I just go over some of the other stuff that some other sources that I think are also helpful in addition to this book. One thing I really want to show you guys is if you look, make sure you look up this video by Tableau. So I went to Tableau conference a couple of years ago, and okay, so it looks like it's not loading, but I went to Tableau conference a couple of years ago, and they had this talk called Data Science Applications with TabPy and R. Basically, Tableau is a BI tool. Basically, it's a visualization tool, more or less. And TabPy is a way to connect Tableau to Python. That way, you can execute machine learning algorithms dynamically and have them display the results in Tableau. And they had this really cool demonstration over here on a PC. I highly recommend watching this video. And they took this car data set, right, with like 10 different dimensions of like engine size, reliability, quality, stuff like that. And and what they did is that they demonstrated that PCA is a tremendous way to actually plot data that, are maybe on 10 different dimensions onto a 2-dimension plane. And what you could do with it is that, and this might be a little bit hard to see. Let's see if I can show you guys the original. What you guys can see over here is that they actually were able to reduce those 10 dimensions into just 2 dimensions and then label every single point. And when they did that, you could start to see patterns with how you could like group your data. So for example, you'll see Chevrolet Suburban, GMC Yukon, Nissan Pathfinder, Armada, Lincoln Navigator Luxury. These are all massive American cars or massive cars made for the American market. And they're all in this corner over here. The Acura MDX, I believe, is an SUV. It's not a massive one, but it is an SUV. And even the Nissan Pathfinder, like that's not an American car, but it is a massive SUV if you've seen it. And like if you see the way the Nissan Pathfinder looks, you're like, oh, this was designed to look massive. And you'll see those are all in this corner over here. Really fast German luxury cars are down here. So your Mercedes CL600s, your AMGs, your Porsche 911s are like down in this corner. And I believe, yeah, your really efficient Asian cars, so Camrys, Kias, Nissans, Priuses are kind of in this area over here. And this is tremendous because imagine you're talking to a business owner, right? Or like someone in business that you need to talk to. And this is what really got me into PCA when I first saw it. What they did is that they took 10 different dimensions, so 10 different columns of data, crushed it down to just 2. And this is something you can show to a business person and say like, oh, these cars are kind of similar. These cars are kind of similar. Now, you're probably looking at this being like, oh yes, of course, massive cars are similar to each other. Efficient cars are similar to each other. But what if this was something to do with customers where the data was less obvious that was the case? That's the beauty of PCA. That's one of the beauties of PCA. You can do 2 different things with it. You can reduce the amount of data you have to process for your machine learning algorithms, and you can reduce the data into 2, 3, or 4 dimensions, which is something that can be plotted. And you might be wondering, how do you plot 4 dimensions? It's not, you technically can't, but what you can do is you can plot 3 dimensions and then color every single point, and the color would be the 4th dimension. And what they did over here is they did a 2-dimensional thing and then had the color be the value of the PCA. So given that this is still running, I don't believe we're going to get some great results because we're at, what, 5 minutes now? So I might want to just kill it, or we'll keep it running, and let me show you guys what I have in this notebook over here. And this is the notebook I have in my Patreon, but I'll go through the entire thing with you guys right now. So it's the same basic stuff. The code's just a bit cleaner because I wasn't doing it live. And what you'll see over here is as we go down, I have an entire section where I start plotting out the data and I start showing how you can use Plotly. So, whoop, to start plotting out data to show which transactions are fraudulent and which ones aren't. So let's take what happened is we took those 31 dimensions and then I crushed it down to just 3. And then I colored the fraudulent transactions yellow and the non-fraudulent ones blue. Oh, and this is just a sample, but let me go ahead and remove this sample method over here. So we'll do that. Save. This is still running. Let's kill it because it is, yeah, it's just hogging all the resources. Run everything. And you'll see what we have over here. And the reason I'm not live coding this is because, I do want to, I think the video is stretching to about 45 minutes right now. What you will see over here if it decides to run. Oh, what error do we have? Ah. All right, let's run everything now. Oh, shoot. Interrupt it. I have the same code over here that I want to get rid of. Okay, so you can see over here, Plotly is now plotting the data. And you can see Plotly is super easy to use. You just import plotly.express as px, and then you define your figure, which is px.scatter3d, and then you give your data set and then the names of your columns and then the color I want it to be class. And you'll see over here, yellow is fraudulent, blue is non-fraudulent, and you can see it's very obvious that our fraudulent transactions follow a very specific pattern over here. I've taken 30 dimensions of data, crushed it down to just 3, and now I can show a stakeholder and I can say, hey, look at this. It's obvious our fraudulent transactions all fit a very specific pattern of data. And if I wanted to plot, this is just plotting the fraudulent one. So you'll see, if you look at this, this is just our fraudulent data. It's obvious that it follows a very specific pattern as to how fraudulent people decide to, spend the money or however, fraudulent transactions work. And to me, this is the real, this is the big beauty of PCA. And you can see non-fraudulent transactions kind of had this V shape that it's a little bit hard to see because I didn't outline every single point. I would probably put this into some a better visualization tool like Tableau or something if I really wanted to visualize it, but this just gives you an example of how to handle that. But as you can see, probably more importantly than anything, it's obvious that fraudulent transactions follow kind of this cone that starts down here and goes all the way up here, and then we can start breaking this down into smaller and smaller components and different to explain okay, which variables are the ones that are explaining that. So that's kind of what we're doing. That's in my opinion, the beauty of dimensionality reduction and really what we're doing over here. And then finally, they go over locally linear embedding. They don't really go over any of the actual concepts inside. It basically you just perform k nearest neighbors, and it tries to reconstruct the data based through the relationship that every point has to every other point, and put that onto plot all of that onto a lower dimensional space. So, but they didn't really spend much time on it. So I'm guessing that PCA is what they really want us to focus on. So that's chapter 8 for you guys. I tried to bring this video out a little bit faster, and as you can see, I'm shooting a little bit differently than I normally do. But if you have any questions or concerns, please leave them in the chat below. I'm trying to put out these videos a little bit faster than I normally do because I really I just love learning this stuff and love passing down knowledge to you guys. But thank you guys so much for joining. Again, if you haven't already, make sure to like, comment, and subscribe on the video. It's a great way to support my work. Patreon is another great way to do that as well. The notes will be available over there, but as you can see, I displayed all of the notes on this video. I'll just do a quick run through of them again in case you want to screenshot them for your own convenience. And then we'll do the same thing with the Python code as well. And that's about it. Thank you guys so much for joining me, and I hope you have a good day.